If you had to guess the shape of a freestanding arch, what would you say? A parabola? Let's try and fit a parabola to the shape of the St. Louis Gateway Arch. It's close, but not quite. So maybe it's some sort of elliptical segment? Not really. Well, the shape of a freestanding arch actually comes from the shape of a hanging chain or cable. Now, the shape of a hanging chain is actually very useful for building arches, because a hanging chain is in perfect equilibrium, meaning the chain's own self-weight is perfectly balanced by the pure tension forces in the chain. So, if we flip this shape vertically to make an arch, the arch's self-weight would similarly be perfectly balanced by the pure compression forces in the arch. That means there's not going to be any bending, no shear, and all that without the need for external supports. But that then begs the question: what exactly is the shape of a hanging chain? Well, as I mentioned earlier, a hanging chain is in equilibrium, so we can apply an equilibrium analysis to the chain. Due to symmetry, we only need to analyze one half of the chain. So let's cut our chain in half and draw a free body diagram of the chain as a thin curve of uniform density. At A, there will be a tension force TA acting to the left. Meanwhile, at B, there's another tension force TB acting at some unspecified angle theta from the positive x direction, such that TB is tangential to the curve at B. Finally, we also consider the weight force of the chain acting downwards. The weight force of the chain is just mu times g times s, or the linear density of the chain times the acceleration due to gravity times the length of the curve. We can now write our equilibrium equations. The net force in the x direction is 0, so minus Ta plus Tb cos theta equals 0. And the net force in the y direction is also 0, so minus mu gs plus Tb sin theta equals 0. We can then combine both equations to give mu gs divided by Ta equals tan theta. Now, to make our calculations easier, it becomes convenient to write Ta divided by mu g as some special constant. Let's just call it A. So S divided by A equals tan theta. Now, if we were to zoom in infinitely at point B, the curve of the chain becomes indistinguishable from its tangent line. At that scale, a tiny step along the curve can be represented by the right triangle with horizontal side dx, vertical side dy, and hypotenuse ds, as well as the same angle theta measured from the positive x direction, since, as I previously mentioned, TB is acting tangentially to the curve at B. Based on our tiny right triangle, dy by dx equals tan theta. And if you have ever taken a calculus class, this relation should come as to no surprise to you. So dy dx equals s over a. But we're not done with our tiny right triangle just yet. Using Pythagoras theorem, it's a right triangle after all, of course we're going to use it, ds squared equals dx squared plus dy squared. We can then rearrange this equation, take out a factor of dx squared from the radicand, and substitute dy dx equals s over a back into the equation to get ds equals the square root of 1 plus s over a squared times dx. We now have a differential equation in terms of the variables s and x, which we can solve by separation of variables, s on the left and x on the right. This leaves two integrals to solve. The only tricky maths here is maybe the integral on the left, but any calc student worth their salt should know that this integral is just begging for some kind of substitution. In this case, we can let s equal a sinh u. So, on the left, we have 1 over the square root of 1 plus a sinh u over a squared times a cos u, integrated with respect to u. Next, using the hyperbolic identity that cos squared u minus sinh squared u equals 1, the radicand will simplify to cos squared u. And when it's all said and done, everything nicely cancels out and we're left simply with the constant a, which when we integrate gives au plus h equals x, where h is our constant of integration. Remember how s equals a sinh u? Well, that also means that u equals inverse sinh s over a, and consequently a inverse sinh s over a equals x minus h. we can rearrange this equation in terms of s over a, which as we recall is also equal to dy dx. So, dy by dx equals sinh x minus h over a, and therefore the antiderivative, y, is a cosh x minus h over a plus k, where k is some other constant of integration. These constants, h and k, are used to translate the curve horizontally and vertically respectively, depending on the boundary conditions. That means that the shape of a hanging chain is not a parabola, but a hyperbolic cosine, also known as a catenary curve, stemming from the Latin word catena, meaning chain. So, the shape of a freestanding arch would just be an upside-down hyperbolic cosine, or catenary. If we come back to the St. Louis Gateway Arch, we can indeed see that a hyperbolic cosine fits the shape of its curve, although technically, the Gateway Arch is defined as a weighted catenary curve, given by b cosh x over a, and not a cosh x over a, since it doesn't have a uniform weight along its curve. Notice how the bottom is thicker than the top. But hang on, I hear you say. No, I've definitely seen freestanding arches that don't look like a catenary curve. I mean, I've seen semicircles, horseshoes, pointed ones, basket handles, weird offset ones, you name it. The truth is, while these arches may not look like a hyperbolic cosine, the hyperbolic cosine is still crucial in their construction, because for a freestanding arch, its line of thrust, which is the line along which the force travels, is always going to be a hyperbolic cosine. And so long as the line of thrust remains within the overall shape of the arch won't collapse under its own weight. And that's why the ideal freestanding arch is in the shape of a catenary, since it minimizes the material and costs needed to build the arch.